Hello and welcome. This video is part 3 of our basic skills mathematics review, and in this video we're going to look at operations on real numbers. Most of the numbers we will be encountering in algebra and more advanced courses are going to be integers and rational numbers, in other words simple fractions, and because of that in this video we're going to focus mostly on those types of operations, but the skills that we learn are applicable to all kinds of real numbers. So but most of our examples will focus on integers and fractions. We'll go ahead and start with integers. When it comes to operating on integers, there are two sets of rules that we need to learn, and once we have those in place, we can simplify arithmetic expressions of any level of complexity by applying these two sets of rules. The first set of rules we'll be looking at are the addition subtraction rules, and the best way to learn those is by looking at some examples. For example, we know that when we have two positive numbers or two negative numbers that are being combined, the outcome is going to be more of the same, right? So here it's going to be a more positive result, meaning a larger positive result. Here it's going to be a basically larger negative result. By that we mean further away from zero toward the left, right? So basically the correct way of putting this would be actually a smaller, but we mean the absolute value is going to be larger in the sense of distance from zero. All right, so basically if we're combining two numbers with the same sign, we're going to add their absolute values and we're going to keep the common sign, right? You see that? So here we add the absolute value of -2 and absolute value of -5, which are 2 and 5, we get 7. We keep the common sign, which is negative. If we are combining numbers with opposite signs, however, what we're going to do is we're going to take the absolute value of the smaller one. So here the one with the smaller absolute value is the better way of putting it, which would be this one, right? And we're going to subtract it from the absolute value of the larger one, and we're going to then take the sign of the larger one for the result. So when we take 2 and subtract it from 5, we get 3, and we're going to use a positive for the result because the larger number here was positive. And in this case, notice it's going to be a very similar situation. So we're going to take the number with the smaller absolute value, which is 2, and subtract it from the number with the larger absolute value, which is the -5. We end up with 3, but we're going to use the sign of the larger the number with the larger absolute value as the sign of the result. Okay, which all should make common sense to you as well. So with this one, imagine that you let your bank account get overdrawn and it's at a balance of -$2, and then you deposit $5. So what's your balance now? See, money interactions or transactions are a good way of making sense of why these rules work the way they do, right? Or let's say that you had $2 in your bank on a given day, in a certain account, of course, and then you wrote a check for $5, and the bank, knowing you, honored the check. However, that would take your balance to what? To a -$3 situation, right? And here again, let's say you have $2 in your account, you deposit $5, you'll end up with $7, right? And if you're overdrawn $2 and you write a check for $5, which gets honored because of your reputation, then you'll be at a balance of -$7. So these are the ones that confuse people the most. So make sure that you understand those simple rules. So I broke them down into same sign case and the opposite signs case, right? The same sign case, when combining two numbers with the same sign, basically you're going to add the absolute values and you're going to keep the common sign, right? And if they have opposite signs, you're going to always subtract the smaller, the one with the absolute value of the smaller number from the absolute value of the larger one, and you're going to then take the sign of the larger one for the outcome. So here the sign of the larger number would be negative, here it would be positive, etc. Now, multiplication and division rules are much simpler than these, right? With these, if you multiply, there's a nice table you can make here because of the simplicity. Notice that it works with both multiplication or division, and division, I guess I mean. All right, so when you multiply or divide two positive numbers, the outcome is always going to be positive. And when you multiply or divide two negative numbers, the outcome is going to be positive as well. If you multiply a positive number by a negative number or a negative number by a positive number, you're going to get a negative result. So if you're going to put it in words, you get a positive result whenever you multiply two numbers with the same sign, whether they're both positive or negative, and you get a negative result whenever you multiply two numbers with opposite signs. Make sure you completely know all of these basically 4 rules, and then we should be able to proceed very smoothly with any kind of complex operation. All right, let's go ahead and give these a try. As always, your best bet is to try everything on your own first. You'll be surprised how much you may already know. And then come join the video again so we can make sure that we got the same answer. All right, so for the first one, we have 3 minus 17. And basically, we're combining two numbers with opposite signs, so we're using the addition subtraction rules, and we're going to take the number which has a smaller absolute value, subtract it from the number with the larger absolute value. So 3 from 17, we get 14. And remember, we're going to, for the result, take the sign of the number with the larger absolute value. So here it would be the -17, and the sign is negative. All right, so in this case here, we are going to be eventually using these rules, but first we need to deal with this situation and get rid of the parentheses if possible. So remember that when you see a parenthesis like that, that's going to be a multiplication, a hidden multiplication here. The number that is hidden is this 1 here. We call it the invisible 1. So we're going to go ahead and take care of this multiplication here. That will get us -2 plus 8. And when we do this, we're going back to these rules now, right? Combining numbers with opposite signs, we're going to take the absolute value of the smaller number and subtract it from the, well, we should say that absolute value of the number with the smaller absolute value and subtract it from the number with the larger absolute value, and we'll end up with 6. And for the overall sign, we're going to take the sign of the larger number, or the number with the larger absolute value, we should say. Okay, like so. So the answer Now, even though it's positive 6, we usually are just going to type in 6 in homework systems such as MyMathLab, etc. All right, so in here, notice that we are combining two numbers with the same sign, so we're just going to combine the absolute values 12 and 8 and we get 20, and we're going to keep the common sign, so we get negative 20. Here, make sure that you don't ignore the 0. 0 is a number like any other number, so we're going to keep the 0 and we're going to go ahead and multiply those, and we know that negative times negative is positive, so we end up with 0 plus 10, and that of course is just 10. So here we have negative 10 minus 0, right? And that just gives us negative 10. Notice that 0 minus negative 10 and negative 10 minus 0 don't give us the same outcome. That's because unlike addition and multiplication, which are commutative operations, meaning a plus b equals b plus a, and a times b equals b times a, the same cannot be said about subtraction and division. In other words, a minus b does not necessarily equal to b minus a. Now, it's very important to understand that when we say something is not true in mathematics, we don't mean always. We mean there's at least one place where it fails, right? Otherwise, you may get a scenario where a minus b equals b minus a. Can you think of a scenario, values for a and b, where a minus b may be equal to b minus a? Think about that. When do you think that would be? If you said when they're equal, you would be right, because think of it this way. What if a and b are both 3's, right? Then you get 3 minus 3 and 3 minus 3, so they would be equal. However, for other cases where the two numbers are not equal, they wouldn't be the same, right? Like for example, let's say a is 3 and b is 4. So we get 3 minus 4 here, which is negative 1, and we get 4 minus 3 here, which is 1. Okay, so, and of course, because it fails once, we generally say this does not hold as a rule. Therefore, the subtraction operation is not a commutative operation. And the same goes with division. A divided by b is usually not equal to b divided by a. So make sure that you don't make the mistake of treating these two operations as you do with these two operations. By the way, notice these two operations are related. Multiplication is just repeated addition, so are these two. Okay, in fact, division is repeated subtraction, right? You may have heard of this one, but some of you may not have heard of this one, but it's true. Like when you do 8 divided by 3, right? It's like taking 3 away from 8, that leaves you what? 5. And it leaves you, so we notice that there's still a 3 left in that, so we can take another 3 away and we get 2, right? And we are done now, right? So that's why we have 8 divided by 3. So we normally do this long division like this, right? But notice that's just repeated subtraction, right? So how many 3's were we able to take out? 2 3's, right? And at the end we were left with what? 2. So there it is, same result. So 2 and 2/3. That's it. All right, so that's simple enough, but very, very fundamental and important. All right, go ahead and give these a try and then come back and join us. All right, welcome back. So here, notice that we're going to deal with this multiplication and this one first. Negative times negative is positive, so we end up with a 3. And then we take care of this multiplication as well, and that gives us plus 15. Okay, so that's simple enough. We know that's going to be 18. Now over here we're dividing, right? We're dividing two numbers that are both negative, and we know that when we divide or multiply two numbers with the same sign, we're always going to end up with a positive answer. So the answer is going to be positive 5. And of course, we're just going to use 5 if we have to enter it into any kind of a system. All right. Okay, now that we are comfortable with operations on integers, let's go ahead and take a look at operations on fractions. Before we can really successfully do operations on fractions, we need to do a little bit of prep work. We'll go ahead and start with the fundamental concepts of divisibility, factors, and prime factorization. A natural number A is divisible by another natural number B if the remainder of the division of A and B is 0. So for example, we know that 3 goes into 12 4 times with a remainder of 0. Therefore, we say that basically 12 is divisible by 3. We can also say that 3 goes into 12, right? Or that 3 is a factor of 12. So all these are equivalent ways of expressing the same fact. One group of numbers that play an important role in what we will be doing the rest of the term is the group of prime numbers. A natural number greater than 1, the key phrase here being greater than 1, because we do not want to be considered prime, whose only factors are 1 in itself, is called a prime number. That means the number is only divisible by 1 and itself. Now, if a natural number larger than 1 is not prime, then we call it a composite number. So one other way of defining the prime number would be exactly based on divisibility, right? A natural number greater than 1 that is only divisible by 1 in itself is called a prime number. So again, two equivalent definitions, they get the exact same point across, right? So here are the first few prime numbers: 2, 3, 5, 7, 9, etc. As you can see, one of them has been marked in red. Let's see if there's a reason for that. So why is 2 written in red? Well, 2 is a very special prime number, okay? For one thing, it's the very first prime number, right? Because remember, prime numbers are natural numbers greater than 1. So what's the first one you come to? Remember, we're not dealing with the continuum of real numbers. We're only dealing with natural numbers now, right? So what's the very next natural number? 2. So it's the very first prime number. Notice it is only divisible by 1 and itself. It is the smallest prime number, obviously, but the most important aspect of it is that it's the only even prime number. So why would that be? Think about it for a minute. Can you tell me why 2 is the only even prime number? Why can't any other even number other than 2 be prime? Well, let's look at say one like for instance 6. That's an even number. Why can't that be possibly prime? Because remember, If it's a even number larger than 2, then it's going to be divisible by, that's it, 2. So therefore it cannot be prime, and that's why 2 is the only even prime number. Next, we need to understand the notion of divisibility rules, and the three most significant ones that we'll be dealing with are divisibility by 2, by 3, and by 5. Okay, and the rules are pretty simple. The divisibility rule for 2 is the fact that a natural number is divisible by 2 if it is even. As simple as that. Now, another way of saying even is that it ends in a 0, a 2, a 4, a 6, or an 8. So here are a few examples of numbers that are divisible by 2. What do they all have in common? They're even, right? They end in a 0, 2, 4, 6, or 8. Divisibility rule by 3 is not as simple as that, but it's not that complicated either. What you need to do is to find out if a number is divisible by 3, you need to add all the digits. Okay, so like 4 plus 1 plus 5, etc. 1 plus 2 plus 3 plus 6, etc. So if we look at these, let's determine which ones are and are not divisible by 3. Look at this one. 4 plus 1 is 5 plus 5 is 10. Now, if once you add the digits, that sum is divisible by 3, then the number is divisible by 3. So 415 would be actually a number not divisible by 3. How about 1, 2, 3, 6? Is that divisible by 3? Well, let's see. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 6 is 12. So yes, this one is divisible by 3. How about this one? Look, that's a huge number, isn't it? But it doesn't matter, because when we start adding the digits, these aren't going to contribute anything to the sum, right? Adding 0 doesn't really change the sum. So it's just 1 plus 1 plus 1 that matters. And what is 1 plus 1 plus 1? That's 3, right? So this one too, yes, it's divisible by 3. So the first one, no, because the sum of the digits was not divisible by 3, because the sum of the digits was 10, and 10 is not divisible by 3. But these two, yes, because they added up to their digits added up to numbers that were divisible by 3. Divisibility by 5, almost as simple as divisibility by 2. Even simpler, because if you want to know if a number is divisible by 5, all you have to check is that it ends in a 0 or a 5. That's it. You don't even have as many choices as you did for 2. So if it ends in a 0 or a 5, it's divisible by 5. You can be certain of it. Okay, so here are a few examples of numbers that are divisible by 5. Next, we're going to look at the concept of factorization. When, for example, we multiply 3 and 4 to get 12, we call both 3 and 4 factors of 12, right? Because of how we defined factor earlier. If a number goes into another number, we say it's a factor of that number. We also call 3 times 4 a factorization of 12. So each of these is a factor of 12, and because their product gives 12, we say this is a factorization of 12. Note that 12 has other distinct factorizations. For example, one is the one we just discussed. Here's another one, 1 times 12. Perfectly good factorization, and sometimes the only one that can help us. And if we do call it the trivial factorization, don't let the name lead you into thinking that it's not significant or important. It is, but it's trivial in that it's a very simple one to come up with, right? 12 can also be written as 2 times 6, right? And you don't even have to write the factorization, doesn't even have to have just two numbers in it. Here is a factorization of 12, right? As it turns out, this is the most important factorization of 12. Why? Because take a look at each of the numbers in it. What are they? They're all prime. So that's why we call this the prime factorization of 12. And we're going to be playing with the prime factorization of numbers quite often. So make sure you understand prime factorization well. So here we reiterate that of the 4 factorization of 12, 1 is very important to us because it allows us to write a number in its most raw form as a product of its unique prime factors. It's the one that we mentioned last on the previous screen. And notice that each of these numbers is a prime. There could be a repetition, that's not a problem, but notice they're all prime when you look at the factors. Now let's learn a simple algorithm that will help us find the prime factorization of a number in a cleaner, more mature way than the factoring tree that we used to use back in K through 12. The factoring tree, of course, works fine, except if you want a much more efficient method, we can do what follows. All right, let's say I want to find the prime factorization of 36. Okay, so I'm basically going to write 36 and I'm going to draw a line right to its left. So something like that. And now what I'm going to do is I'm going to do the following. I'm going to start asking myself one question repeatedly. Looking at this number on the right, I'm going to say, what is the smallest prime number that goes into that, right? And remember, since it's even, that's a no-brainer. 2 goes in every even number, and 2 is prime. So on this side here, you're only going to want to write prime numbers. So we write 2 here. Uh-oh, I'm still on the line tool. Give me 1 second. Okay, here we go. So 2, and I'm going to go ahead and divide. 36 divided by 2 is 18. I'm going to write the result here. Now, what am I going to do next? Exactly what I just did. I'm going to keep asking that same question. What is the smallest prime number that goes into that number on the right, right? And again, as you can see, it's even, so it's going to be 2. So we divide again, 18 divided by 2, 9. And again, we ask the same question, what's the smallest prime number that goes into 9? This time we know it's 3, not 2, right? So we go ahead and divide. We get 3. Now look, we have a prime number over here. So when you ask the question, what is the smallest prime number that goes into it, you can get a little bit more general and say, what is the smallest prime number that goes into any prime number? Think about it. It's going to be itself, right? So at this point, we put 3 and we get done. Once we arrive at that 1, we're done. So as soon as you see the 1, you're done, okay? Now, the beauty of this and the fact that you kept asking what is the smallest prime number that goes into the number on the right is that in the end on the left, you have precisely the prime factorization of the number you were looking for. So we can say 36 equals 2 times 2 times 3 times 3. Or we could use exponential notation, which is the more general usage, and say that's 2 squared times 3 squared, like so. Okay. And that's how you find the prime factorization of a number. So here's one for you to try. Go ahead and use the same technique that you just learned to find the prime factorization of 3200. It'll be quicker than you actually think. Go ahead and try it. All right, so here we have 3200. It's an even number, so we know we can start with 2 because it's the smallest prime number that's going to go into that number, right? So we go ahead and divide, we get 1600. Again, what's the smallest prime that'll go into 1600? 2 again, right? We divide, we get 800. Again, we know we can stay with 2, and you need to as long as you can. And we get 400. And 2 again gives us 200. 2 again, 100. 2 gives us 50. 2 again, 25. And now we have to stop with 2 because 2 doesn't go into 25 anymore. So now we have to go to what? To 5. So 25 divided by 5 is 5. And then finally, what's the smallest prime number that goes into 5? Well, that's prime, so it's going to be itself, and we get 1. Now we're done. And look, we have this beautiful prime factorization of 3200, so we can say 3200 is equal to, that was terrible, let's try that again. So 3200, I'm using this tablet, I'm not writing directly on my screen, so it's taking me a little bit of time to get comfortable with this, so it'll get better. Just take, what I have. So I could write 2 times 2 times 2, etc. So, but it's easier if I write there's 2, 4, 6, 7. So there is 1, 2, 3, 4, 5, 6, 7 factors of 2. So 2 to the 7 times there's 2 factors of 5. All right. Of course, we can double check that if we want, but the procedure needs to be shown, okay? But checking it on a calculator is fine. So we have 2 to the power of 7 times, oh, I need to get out of that exponent position, so times 5 squared. And when I hit enter, I better see what? 3200, which is exactly what we see. All right, so that's a really nice, efficient way of finding prime factorization. Make sure you practice that. All right, next come the extremely important concepts of GCF and LCM. And even though one stands for greatest common factor and the other for the least common multiple, there is an interesting relationship between the two that I would like you to understand as well. So first we'll go ahead and formally introduce the two concepts, and then we'll show a nice graphic that'll show how they're related. So the GCF of two real numbers x and y is the greatest common factor of x and y. So what does that mean? That means it's the largest number that goes into both x and y. Now, also for two real numbers x and y, the least common multiple, or LCM, of x and y is the least common multiple of x and y. That's all it is. And what is that? That means the smallest number that both x and y go into. So let's take a look at an example. To demonstrate, we can use the real simple situation with 6 and 9. We know that the largest number that goes into both 6 and 9 is 3, so that'll be the GCF of 6 and 9. And we also know that the smallest number that they both go into is 18. So this arrow diagram really helps us understand the relationship between the GCF and LCM. On one extreme, we have the greatest number, or the largest number, in this case 3, that goes into both of those numbers. And on the other extreme, we have the smallest number that both of those numbers go into. That is the nice relationship between GCF and LCM. They're the two significant numbers related to any pair or group of natural numbers. So we can make a general case of this. So if x and y are any two natural numbers, then the GCF again is the largest number that goes into both of them, and the LCM is the smallest number that they both go into. All right, in this next example, we're going to try to find a procedure to find the GCF and LCM of these two numbers, 36 and 60. And then we're going to provide an arrow diagram that's going to show the relationship between the GCF and the LCM. Do try to do this on your own. I think you will be able to handle this, but do come back to check to make sure we're on the same page. Okay, so we go ahead and start by looking at the most fundamental structure of each of these numbers, and we know that the procedure that helps us find that is the prime factorization procedure. So we go ahead and ask ourselves, what's the smallest prime number that goes into 36? That of course is 2. And then we write the result of the division of 36 by 2 below 36, and we repeat the process. What's the smallest prime number that goes into 18? That's 2. That leaves us 9 when we divide, and then we have to go to 3. 9 divided by 3 is 3, and then finally 3 goes into itself once. We know that once we hit the 1, we're finished, because we know that we can't get 1 on this side, because on this side we only have primes and 1 is not prime. Of course, 1 is not composite either. 1 is neither of the two. It's a special number, right? So we'll deal with 60 now. Again, it's even, so we can start with 2. We know that we get 30, and then that's even again, so 2, 15. Now this is not even, so we have to move on to another number. So 3 here, 5, and 5, 1. It would not be wrong if you wrote 5 first and then 3. You just wouldn't have this nice order from smallest to largest. You see, that's the only reason we say that. So let's go ahead and write those numbers in their prime factored form. So we have 36 equals 2 times 2 times 3 times 3, and we have 60 equals 2 times 2 times 3 times 5. Now, if we want the GCF, remember that's going to be the greatest common factor. So we notice that we have 2 in common here. So both of those are going to be part of the GCF, and we have a 3 in common. So we just get 2 times 2 times 3, right? So 12. All right. So now for the LCM, we know we're going to have a number large enough that can handle both of these numbers. So that's definitely going to need all of those factors in it, right? But it's basically going to need another 3 and then a 5 as well. So if we write these numbers in exponential form, we get 2 squared times 3 squared and 2 squared times 3 times 5. So for the LCM, what you're going to do is you're going to pick the highest power of every factor that you see and you're going to multiply them. So we're going to get 2 squared times 3 squared times 5. And that's going to be 4 times 5 is 20 times 9 is 180. See, a really nice simple procedure that'll give us, without the shadow of any doubt, the GCF and the LCM. Now, for the GCF, one way of thinking about it is that if you have this exponential form, you're going to multiply the lowest power of only the common factors, right? Notice the lowest power of 2 is 2 squared itself, and then lowest power of 3, which is a common factor, is 3, and we don't need 5 at all because it's not a common factor. So the procedure for finding GCF is we're going to multiply the lowest power or powers of common factors, and the procedure for the LCM is that we're going to multiply the highest power of all factors, because remember, it needs to be large enough so that they both go into it, right? So very simple, very powerful procedures, right? So again, the two numbers here in the under discussion are 36 and 60. Now we know that the number, well, we should say the largest number that goes into both of them is going to be 12. That's going to be the GCF. And the smallest number, let me go ahead and finish that first. My pen is not cooperating. All right, so we get equals 12. And the smallest number that they both go into is going to be 180. The really nice thing about this procedure is it's very systematic. You can't, go wrong. And a lot of students have a very difficult time trying to come up with this by just guessing, etc. So it takes all the guess out of it, right? You can just go through the procedure and you'll find both the GCF and LCM. So for the GCF, multiply the lowest power of common factors. For the LCM, multiply the highest power of all factors. And that's it. So definitely go ahead and give this one a try before you come back to the video. Try to come up with them on your own first. All right, so here we have two numbers. We start with 240. So this is not going to be as pretty as the last one here. I can actually use the line tool to do a nicer job, at least on the line. So let's go like this. And the other number that we need is 360. All right, so we're going to find the prime factorization of each of those. So for 240, we have 2, 120, 260, 230, 215, 3, 5,
5, 1. For 360, we start with 2, so we get 180, 290, 245, 315, 3, 5, and 5, 1. Okay, so let's go ahead and write 240 in prime factored form. And we can see it's going to be 2 to the power of 4 times 3 times 5. Now for 360, we're going to get 2 cubed times 3 squared times 5. All right, so now we're going to go for the procedure. So for the GCF, we're going to multiply the lowest powers of the common factors. So which factors do they have in common? Well, they have all 3 factors in common, but the lowest power of 2 that we encounter in the 2 factorizations is 2 cubed. The lowest power of 3 is going to be just 3 itself. And the lowest power of 5 they have in common is just one single 5 itself. And when you multiply that out, you get 2 cubed, which is 8, times 5, which is 40, times 3, which is 120. Now, for the LCM, we're going to multiply the highest power of all factors, right? So let's see my pen again. Here we go. The highest power of all factors. So what's the highest power of 2 that we see? Well, it's 2 to the 4. And what is the highest power of 3 that we see? We can see it's 3 squared and then 5. So we end up with 16 times 5, which is 80, times 9, which is 720. All right, so we just found the GCF and LCM for 240 and 360. So if we want to do a quick arrow diagram, we have 240 and 360, and the smallest number that they go into is going to be 720, and the largest number that goes into both of them will be 120. Let's see, this is not cooperating. Give me 1 second to fix this pen. All right, so I think it's working again, and here we have the GCF down here, which is 120. All right, so notice a very simple procedure. Find the prime factorization of each of the two numbers and write it in exponential form. And then for the GCF, simply multiply the lowest power of only the common factors, right? And for the LCM, multiply the highest power of all factors, because it has to be, large enough for both of those numbers to go into. Okay, and that's it. So 720 and 120 in this case. Now, some of you may be thinking, well, I could have come up with that without going through all this procedure. Do I really need this procedure? But you see, the thing with procedures is, yeah, there are certain problems that you can do in your head, but let's face it, if they get much larger than that, most of us at least cannot do it in our heads. And the nice thing about procedures is they give us a way to do it when the numbers are so large we can't just do it quickly in our heads. Also, it is this kind of procedure that's very programmable. So that means when you want to teach a machine like a computer to perform a task like this, this is exactly the kind of process that you have to teach that machine. So it's also very good if you want to pursue that line of work of, say, programming computers, etc. All right, just a few more properties before we move on to dealing with fractions. One of them is the identity property is for addition and multiplication. The identity property of addition simply states that for any real number, that number plus 0 is just the number itself. And we call the 0 the additive identity. And the identity property for multiplication is similar, except it says that for any real number, that number times 1 is the number itself. In other words, for addition, adding 0 leaves the number identical to what it was before, right? Additive identity. For multiplication, multiplying by 1 leaves the number identical to what it was before. So therefore, 1 is the multiplicative identity. The commutative properties of addition and multiplication tell us that order does not matter when it comes to multiplication or addition. In other words, if you add A plus B by starting with A and then adding B, you get the exact same thing as if you were to start with B and add A. So you can start at 2, add 5 units to the right, and you end up with 7. Or you can start at 5 and go 2 units to the right, you'll also end up at 7, etc. So same thing here for multiplication. So if you have 3 rows of 4 chairs each, you're going to get 12 chairs. And if you have 4 rows of 3 chairs each, that's also going to give you 12. So the order doesn't matter here. So A times B equals B times A. I guess on the last example, it would be to say, 3 columns and of 4 each. All right. So just to be consistent. So either 4 rows of 3 each or 3 columns of 4 each. The same thing will be done. Graphically, it looks something like this. So you can set up your chairs like this. So when you say, for example, 3 times 4 is the same as 4 times 3, what you're saying is that, hey, you can count this way. So in other words, 3 rows of 4, or you can count 4 rows of 3, and you're going to end up with the same count, 12 on both of them, like that. That's what I was trying to tell you. It's a little bit harder to say sometimes things that are so easy to show, so might as well show it. The associative properties of addition and multiplication tell us how to deal with situations where we have more than 2 items being added or multiplied. So basically what they end up telling us is that, look, if you're adding 3 numbers, it doesn't matter if you add the first 2 and then take that result and add the third one, or if you add the last two and then take that result and add it to the first one, you'll get the same thing. For example, let's just look at a simple example like 3 plus 4 plus 5, right? Notice that if we do this like this, here we end up with 7 plus 5, and here we end up with 3 plus 9. Initially they look different, but look, they're both what? They're both 12, like that. And the same thing for multiplication, right? If you're multiplying three numbers, it doesn't matter if you multiply the first two and then the result by the third one, or if you multiply the last two and then the result by the first one. Again, we can use the same three numbers. Look at 3 times 4 times 5, and look at 3 times 4 times 5. Notice here you end up with 12 times 5, and here you end up with 3 times 20. Again, they look different, but notice they're both 60, like so. Okay, and that's what those properties are. Now these properties are extremely important because we're constantly using them and taking them for granted. We're not conscious of the fact that we're using them, but we are using them all the time. But as you decide to become more and more capable in mathematics, it becomes more and more important for you to understand the underlying properties. That's how you develop depth into a concept or into a topic. Notice that all the properties we've dealt with so far either deal with addition or multiplication, not both, right? Well, the distributive properties are the first properties that tell us what to do when both operations are involved, because when I write a and then parentheses, that means multiply, right? So these properties tell us how to multiply a number into a sum, basically. So we have two versions. The left distributive property of multiplication over addition. It's a long name, but it basically tells you that it involves both operations, multiplication and addition. Works like this. So in other words, if you have a number and then you're going to multiply it into a sum, and remember, you can have two things here or you can have 2 trillion things. It makes no difference. You would still distribute the a by all of them, right? So you get a times b plus a times c. Now the right distributive property tells you, hey, do the same thing even if the number is written on the right side of the parentheses or the group. You're going to distribute from the right and you end up like the same result. Now together they're called the distributive properties of multiplication over addition. We'll use the distributive property very, very extensively as well. The last group of properties we want to look at have to do with equality. The reflexive property of equality just basically says x equals x for any real number x. In other words, any number is equal to itself. So it's like a mirror image reflection, right? The symmetric property of equality tells you that if two numbers are equal, like a equals b, that means that's going to imply that b equals a as well. So again, there's a symmetry going on here. We call it the symmetric property of equality. The transitive property of equality says, given three real numbers a, b, and c, if a is the same as b and b is the same as c, that's going to imply what? A is also equal to c. Through what? Through b. Through their equality with b. This is an important property. Again, it's used a lot, but we don't really consciously think about it much. Finally, the substitution property of equality tells us that, hey, if you have two real numbers and they happen to be equal, then you can use one for the other in any equation or expression, and vice versa. Or you can use the other instead of the first one.
makes no difference. Okay, in other words, they're interchangeable, and that is basically all the properties we wanted to look at. Now we'll talk about dealing with fractions a bit. The last property, actually, okay, perhaps I just slightly lied. Okay, I said no more properties, but this is a very common property with fractions in particular, is the cancellation property. Basically what it says, if you have a times c over b times c, you can cancel out the c's and just get a over b. Why is that true? Well, we're going to utilize some of the properties we just learned to actually come up with a proof. So because if you have a times c over b times c, you can break this up as a over b times c over c, and that's going to be a over b times 1, obviously, and because 1 is the multiplicative identity, that's just going to give us a over b. Again, something we just take for granted. We always just go from this to this, but here's all the reasoning that's going on behind the scenes, right? Okay, no more properties. Now just applying the properties, because that's what we do in mathematics. We learn properties and we apply them. We also prove things, and anything we've proven we can also use at a later time. So simplifying, which means the same as reducing fractions, using the cancellation property, and prime factorization. These two are very powerful tools that help us do that. All right, so for this next problem, we're going to use prime factorization and the cancellation property to try to simplify these fractions. Of course, they can be done without having to do that, but this is a nice demonstration of the power of these procedures. So if we take 36 and find the prime factorization, here I'm going to go ahead and use this line here for my purposes, so I'll just put 36 here. Now I know that 2 goes into 36 18 times. Again, try this on your own before you watch the rest of the video, always, for best results. 3 gives us 3, and then 3 gives us 1. Okay, so there's the prime factorization of 36. Now we can do the same for 60, so I'm going to start that right below. So 2 gives us 30, and then 2 gives us 15. 3 gives us 5, and then 5 gives us 1. All right, so now we can write 36 over 60 as, now for 36 we're going to write 2 times 2 times 3 times 3, right? For 60, we're going to write 2 times 2 times 3 times 5. Now we're going to use the cancellation property, which basically says you can cancel some of these items, right? So we can cancel these 2's, these pair of 2's, and then those 3's. And that's it. That's the only cancellation that's available to us. So now we're going to realize that this is going to leave us 3 over 5. That's a really nice, effective way of reducing a fraction, and by utilizing the prime factorization of the numbers. All right, we can do the same here with 48 over 320. So let's go ahead and find, let me start further up here. So we'll start with 48. We get 2, 24, 2, 12, 2, 6, 2, 3, and then 3, 1. All right, now let's find the prime factorization of 320, which gives us 2, 160, 280, 240, 2
20 to 10 to 5 and then 5 1. So now we're going to rewrite 48 over 320 using those prime factorizations. So on the top we're going to write 2 to the 1 2 3 4, so 2 to the 4, or it's better in this case if we actually write 2 4 times. It'll be easier to see the cancellation, even though you could use the exponential notation. For this particular task, it's better to leave it in the form multiplied out form like this. All right, so here we're going to, in non-exponential notation, in other words. So here we're going to go with 1 2 3 4 5 6 factors of 2. And then 1 factor of 5. All right, now again, we go ahead and use the cancellation property. Cancel, cancel, cancel. All right, and that's all we can cancel, right? There's nothing else that's going to cross cancel. So now we realize that this is going to end up giving us what we have been looking for. So we get 3 over 4 times 5, which is 20. And that's it. Okay, so a very, very nice application of both prime factorization and the cancellation property. So when it comes to fractions, they're a little bit different from integers in the sense that multiplying and dividing them is easier than combining them, adding them, and subtracting them. So, which is the opposite when it comes to integers, right? So let's go ahead and see how we go about doing these. The rules are, of course, simple. If you have a product of two fractions, you basically can't multiply across, right? Well, that's a nice rule, but the golden rule of multiplying fractions is, yes, by all means do this, but make sure you've done this after these two fractions have been fully simplified. Now remember that you can even cross cancel across from any numerator to any denominator. So always cross cancel and simplify as much as possible before you multiply across. Simplify before you multiply. It saves you a lot of time and effort. Now, for division of two fractions, you keep the first one the same, and then you turn the division into multiplication, and you go ahead and flip this over, turn C over D into D over C. So you invert it, okay? Now, the golden rule for dividing fractions, don't do anything before you turn the division into a multiplication. And once you've done that, then you know what to do. So you're going to invert the divisor first, then you're going to multiply, and before you do that, of course, after you've turned it into a division, you're going to apply the golden rule of multiplication now, which is then simplify and then multiply. Okay? Now, keep in mind that regardless of the problem you're working with on in a math class, your final answer should always be fully simplified. It's not that an answer that is not fully simplified is incorrect. It's just that simplifying, all fractions and expressions provides excellent practice. That's why we like you to always do so. So when we were looking at this, you noticed I wrote y here. So think about why this may be true. And basically, believe it or not, it's kind of an application of the cancellation property that helps us do this. Because let me bring up a blank sheet and I'll show you how this works. All right, so you want to go from being an average student to a power student. Here's the magic word right here, or the magic question. Any student that you see has real depth into any topic and who just naturally does well is the student that has focused more on why, as opposed to those who like to just memorize and focus only on another question, which is what? How. Okay? I get students all the time, just show me how to do it, right? They don't want to know why a certain thing works a certain way. They just want to know how. And as long as you're overemphasizing the how and not the why, you're going to have problems in math. Naturally, the how will follow the why, right? So understanding comes first, and then you realize what needs to be done. So you can't force it the other way around. You can't just memorize a procedure and hope that from that memorization, understanding is somehow magically gonna flow, okay? So make sure you're always concerned with why. All right, so let's take a look at this. Notice that A over B divided by C over D. Well, that's going to be, I think you agree that we can write it as a compound fraction like this, right? Now, here's a nice little application of the cancellation property in reverse, okay? And the way that that's going to work is we're going to multiply the top and bottom of this fraction by the reciprocal of the denominator. All right, so now we notice that, hey, down here, this cancels this cancels this. Well, they just leave you one. So all you have is that numerator, which is A over B times D over C. There, now you know why the division of fraction rules works the way that it does. Always ask why. All right, so let's go ahead and try some of these. Again, try them on your own first. All right, welcome back. So here we have negative 81, which we can, of course, always write it as negative 81 over 1, times, as long as I put that negative on top, I don't need to use parentheses like that, okay? So now I notice that I have some canceling I can do. I know that 9 goes into 9 one time and into 81 9 times. So now see how much easier that's going to be. Who wants to sit there and multiply 81 by 5 when they don't have to? That's the point, see? And if you do this cancellation first from any numerator to any denominator, as long as you're only multiplying, right? Multiplication of fractions is the only operation going on. There's no addition or anything like that, then this works, okay? So now we're going to just get, let's take care of the sign first. Negative times negative is positive. Now, even though we may not type that into any kind of an answer box, we still can write it and it'll help us, hey, we took care of the sign, right? So we get positive, what's left on the top, 45 over 1. So basically 45. So all we're going to write for the answer is 45, like that. Okay. So let's try this one. We have negative 48 over 320. We're going to go ahead and turn that division into multiplication and invert the second fraction. Again, we could proceed and multiply things out as large as they are, but notice how much more efficient it'll be if I don't do that, and if I realize the fact that 40 goes into 320 8 times, it goes into itself 1 time. I notice here also there's a little bit of cancellation. 3 goes into 9 3 times, into 48 16 times. All right, so basically now all we have to do is check to make sure that there's no more cross-canceling possible. And I noticed that I have another pair of numbers I could work with, right? So I'll do 1 second round of cross-canceling, and I realize that 8 goes into itself once, into 16 twice. All right, it looks like we're out of numbers that we can cross-cancel, and that's it. We go ahead and take care of business now. We notice that we have negative times positive is of course negative, and on the top we only have 2 times 1, which is 2. On the bottom we get 1 times 3, which is 3. Okay, now here's an interesting type of fractional division. It's called, as a whole, it's called the complex fraction. Now with these, there is a really nice shortcut which I want to show you, because we're going to use this from time to time, and it'll be nice to know that. All right, so notice that this time we have a over b. Okay, so notice that here we want to look at a over b over c over d, right? So as you know, that means a over b divided by c over d, which is a over b times d over c. Okay, so basically we notice that when we have, let me go ahead one more step, that's AD over BC. So we notice that when we have one fraction divided by another fraction, that's going to be this outer product, AD, over this inner product, BC. Extremely useful and handy shortcut to know. It's going to save you a lot of time when dealing with these kinds of fractional divisions. Okay, so let's see if we can apply that here. Notice we have one fraction over one fraction. Anytime you have that, you can use the shortcut. So we're going to get this outer product, so it's going to be 3 times 16 divided by this inner product, which is 4 times 9. Okay, and of course now we can go ahead and cross cancel as much as we can. We notice that 3 goes into itself once, into 9 3 times, 4 goes into itself once, and into this 4 times. Okay, so now we notice that there's no more cross canceling possible, so we know that the answer is going to be 4 1/3, like that. Okay, and that's how you handle those problems. All right, next we're going to look at combining, which is the general term for adding and or subtracting fractions. When it comes to combining fractions, there are two scenarios that we have to deal with. One is combining like fractions, and the other is combining unlike fractions. Of course, like fractions are fractions that have the same denominator. Unlike fractions, fractions that have different denominators. And the fact of the matter is that to combine fractions, you can only do this. You can only combine like fractions. So if they're unlike, you're first going to make them alike by making the denominators the same. Then you're going to proceed as you did here. So what's the procedure when the denominators are the same? Simple. Keep the common denominator, combine the numerators. Okay? So if you have a scenario in which the fractions are not alike like this, first make them alike, right? So you need to find the LCD, which is BD in this case, and turn both of these denominators into BD. So this one is going to require multiplying by a D. So of course, given that we have to do whatever we do to a denominator to the numerator as well, we have to multiply A by D as well. And here, same thing. We multiply the D by B, so we have to multiply the C by B as well. And of course, we do that so that we're just multiplying by 1 in both of these cases, and therefore not changing the problem, just changing the way it looks. And then we have two like fractions with both having denominators dB, which we keep, or BD, same thing. And we get AD plus BC. And that's how you do those. Very simple. All right, so let's go ahead and tackle these again. Do try them if you think you know how. So this one, again, we're going to go back to our rules, the multiplication, division, and addition, subtraction rules. So we're going to get rid of the parentheses first. So we get -1/6, and negative times negative is positive, so plus 7/6, right? So that's, remember, keep the common denominator and combine the numerators, which is going to give us 6/6, which is 1. And this can happen. You can have two fractions and end up with a whole. And that's, of course, the case here, or combine two fractions, right? All right, so when it comes to this, we're going to take care of that inside the parentheses first, and then we'll deal with that. This is kind of working ahead of ourselves. We're getting ahead of ourselves because we're going to cover the order of operations next, but this was simple enough, so I wanted us to take a look at it. All right, so we get 1/6 minus, we're going to go ahead and take care of the combining of those two fractions. So we get the LCD here being 10. So the 5 has to be multiplied by 2, and the same with the numerator, and the 2 has to be multiplied by 5, and the same here. All right, so now we're going to get -36. Oops, I squared it, didn't I? This happens, but you gotta be alert, you'll catch it right away. So that's -12 minus 1 times 5 is just 5, and that's going to be 1/6 minus, that's -17/10. And of course now that's going to turn into a plus, so that's 1/6 plus 17/10. So Now, once again, we need a common denominator, which is probably 30 here. You can always do the prime factorization and find it if you can't see it so quickly. So the 6 has to be multiplied by 5, and that goes for the top two. The 10 has to be multiplied by 3, and we have to do the same on the top. So we end up with 5 plus 51 over 30, which is 56 over 30. And of course we can simplify that because we know at least 2 goes into both of them, and 2 goes into 56 28 times, and it goes into 30 15 times, and that should do it for us. Okay, there we go. Next, we want to take a look at exponents and powers, and we know about the 4 basic operations of mathematics: addition, subtraction, multiplication, and division. There's a higher order operation that comes right after these, and that operation is exponentiation. Yes, that is a word, and it means exactly what you think it means, and we'll look at it in a minute. And it's closely related to multiplication. As you know, multiplication is repeated addition. So when you say 3 times 2, that means 2 plus 2 plus 2. Use 3 terms, all of them 2, add them up, you'll get 6, right? Exponentiation is repeated multiplication. So if you have 2 to the power of 3 or the third power of 2, that means take 2 and use it as a factor 3 times in a product, and you'll end up with 8. So when you write an expression like x to the n, everything has a name. X is called the base, n is called the exponent, and what that means is use x as a factor in a product n times. So there will be n factors of x, and the way we say that as a whole is we say the nth power of x. A lot of students mistake n to be the power. No, the power is the whole thing, okay? And it's the nth power of x. So let's take a look at what these expressions here are gonna result in. We notice that that's just going to be 5 times 5, which is of course 25. This one, be very careful with, because the negative is not being squared. So what is that going to do? That's just going to carry. The only thing being squared is the 5, so we get something like that. And that's going to be actually negative 25. A lot of students miss this because they see the square, they go, oh, that's going to become positive. No. This one might. Let's see. Because here the negative is being squared, so you're going to get negative 5 times negative 5. The base is negative 5, so here you do get positive 25, which we usually just write as 25. All right, so this next one, by definition of exponents, is going to be 4 factors of 3/4 multiplied out, like so, okay? And of course that's going to be 3 times 3 times 3 times 3 over 4 times 4 times 4 times 4. So that's going to be 9 times 9, which is 81, over 16 times 16, which is 256. All right. So this looks very similar, doesn't it? Except this one, each of these has been raised to the power of 4. And that's exactly what you're going to get if you do this operation, because this is like saying at this point, by definition, this turns into that. Okay, so we know we're going to get the same result. In general, if you have x over y to the power of n, you can just do x to the n over y to the n, and that's how you handle those. All right, so finally we have enough in our toolbox to talk about the order of operations. When we encounter a problem like 2 plus 3 times 5, we need to all agree on handling the situation in the same manner so that we all get the same result. It cannot be that some of us prefer adding 2 and 3 first and then multiplying by 5, and others among us prefer multiplying 3 and 5 first and then adding 2. That is why we need the triple O. That means the order of operations. It works out like this, okay? So we start with parentheses, which of course could mean any grouping symbols, and it could be a nest of them, one within another within another. In case that's the case, we work our way from the inside out, work out the innermost one first, then go to the next level, then the next level, etc. Then we deal with the exponents, so we deal with any powers, and then we get to multiplication and division, which are what we call equipotent. That means neither of these always comes first. Once we get to their turn, we go from left to right and we perform whichever comes first. And when we're done with that and we're only left with addition and subtraction, the same situation. They're equipotent. That means they have the same priority level. So once it's their turn, you just go from left to right and you perform whichever comes first and move on to the next, etc., etc. I know it's been a long video. There's been a lot of ground covered. So we're just going to wrap it up with doing a couple of nice problems involving order of operations, and we're going to call it a day. So notice that when you have a scenario like this, basically treat the numerator and the denominator like two separate problems, and then at the very end we'll let them interact and cross cancel possibly. Don't ever try to cancel out like this when there is operations other than multiplication going on. Okay, so just let's go through and see what we get. So imagine the denominator isn't even there. Focus on this only right now, right? So notice we have multiplication and subtraction. So we're gonna multiply first. So these two will give us positive 48 minus these two will give us positive 12, okay? Over those two are gonna give us negative 4 minus 2, okay? Now 48 minus 12, that's 36 over negative 6. So we end up with negative 6. All right, that's what we had to do there. For this one, again, challenge yourself, try to see what you get, then come back. So as you know, we need to deal with the inside of the grouping symbols first, and within this first one, of course, we're going to take care of the squaring first. So that's 9 minus 2 minus 2 times here we get negative 64 plus 15, and down here we have 3 times 4 plus 4. Negative times negative is positive, so we end up with 4 times 7 minus 2 times Negative 64 plus 15, we know that the operation is subtraction, and we are going to get a negative result because the number with the larger absolute value is negative. So negative, and I believe that's 49 over 3 times 8. All right, so 4 times 7, 28, and negative times negative, positive, so we get plus 98 over 24. Notice no interaction between the top and the bottom yet, just as there wasn't here until the very end where we had just one number over one number and then we cross canceled. So same business goes here. So that's going to be let's see, 20 and 90 is 110 and 16, so 126 over 24. Now let's go ahead and take a look at that using a different screen. All right, so we have 126 over 24. Notice our good old technique can help us here. We're going to find the prime factorization. 2, 63, 3, 21, 3, 7, and 7, 1. 24, of course, gives us 2, 12, 2, 6, 2, 3, and then 3, 1. So now we can go ahead and replace 126 with 2 times 3 times 3 times 7, and the 24 with 2 times 2 times 2 times 3. Okay, now we can cross cancel. We know that we can cancel these two. Those came in from my other screen. Let me get rid of that. And these two. And we know that we can cancel that 3 and that 3. And that should be it. So we end up with 21 over 4. And that's all we have to do for that one. All right, so here we can say 21 over 4. And that brings it to a wrap for this very long but important video. So stay safe until our next basic skills video.